Welcome back. Now we've created a prop class and we're ready to actually render the prop class to the screen. This is going to involve the world position of the prop, that vector we called world pos, and we're also going to be using the knight's world pos as well. Let's dive in. Now we've already seen that our map pos is equal to the negative value of the knight's world pos. Map pos is calculated. It's derived from the knight's world pos. Now let's say our knight starts off with a world pos of 0, 0. Now we can think of the knight's world pos as the location of the screen itself. So the upper left corner is at 0, 0. Now let's say we have a prop that has this rock texture and we give the prop a world pos of 0, 0. So this rock is expected to be at the top left corner of the map and stay on the map even as the knight runs around. Now let's say our knight moves down and to the right, and now the knight's world pos is 1, 1, which means the map pos is -1, -1. So the map has moved to the left and up. Now we would expect the rock to move to the left and up along with the map. So there is some vector that describes the location that the rock should be drawn on the screen. Let's call this screen pos. And that value of screen pos for the rock is going to be equal to the rock's world pos plus the map pos, since it needs to be moved along with the map. So if map pos is -1, -1, then the rock's screen pos is going to be equal to its own world pos plus that -1, -1 vector. So effectively, it'll be stuck to the map. Now, since we know that we can calculate the screen position for the rock by taking its own world position and subtracting the knight's world position, let's see how this works if the rock starts off at the bottom left of the screen like this. Say the knight moves a little bit, changing its world position by this much. This is the knight's world position vector. Well, we could take that knight's world position vector and flip it by scaling it by -1 and adding that to our rock's world position, and then we have the correct screen position for the rock. We're going to need to use this concept when we render the rock. Say we create a function on the prop class called render. And for an input parameter, we'll use a vector for the knight pos. So in the render function, we're going to need to calculate the screen position for the prop using the prop's world pos and the knight's world pos. So here's your challenge. Create the render function for the prop. This function will take a vector2 input for the character's position. Call this knight pos. Now set the value of screen pos using its own world position, world pos, and the character's position, knight pos. Now since we know that screen pos is equal to world pos minus knight pos, we're going to need to use the vector operation vector2 subtract, which also means you're going to need to include raymath. Once you're done, in the render function, use drawTextureX to draw the texture. Then, create an instance of the prop class in main.cpp and call render in the while loop. Now, when you create an instance of the prop class, pass in vector2 with braced initialization to create a vector2 value with 0, 0 for its values, and for the texture, simply call loadTexture and use naturetileset/rock.png. Don't forget to include prop.h. Pause the video and do this now. So here we are in the prop class. We're going to need to create a public function called render. So let's create this. It's going to return void, and it'll be called render. And we're going to use a vector2 input parameter, and we'll call this knight pos. Now let's go ahead and create the function definition for this in prop.cpp. So just under the constructor, we'll create the function and we'll fully qualify the function name using prop with the scope resolution operator. Now we can calculate the value of screen pos. So let's make a local variable of type vector2 called screen pos. And we can initialize this using vector2 subtract. And the arguments are going to be world pos, and we're subtracting knight pos. Now, we need to include raymath in order to use this vector operation. So let's include raymath.h. Now we have screen pause and we're ready to draw the texture. So let's call draw texture x. First, we need the texture and we can use texture. For the position, we're going to use screen pause. That way we draw the texture at the correct position. For rotation, we're going to use 0.f, and for scale, we're going to use our scale member. And for color, we're just going to use white. Now we're ready to create an instance of the prop class. Let's go to main.cpp and include prop at the top here. So include prop.h. Now let's create an instance of the prop class just under the night variable. So we'll say prop, and let's call this prop rock. We're going to use braced initialization, and we need two input parameters here. The first is a vector2 called pause. So we can use a vector2 constructor, and the second input parameter is a texture. So we're going to call load texture, and we're going to load nature underscore tileset slash rock.png. So now we have an instance of the prop class called rock. Now we need to call render, and we'll do this in the while loop. So just after we draw the map, we can render the prop. Let's say rock.render. And we need to pass in the night's world position. So we're going to pass in night.getWorldPause. Let's go ahead and hit run and start debugging. Okay, so there's the rock, and as we move, the rock moves along with the map. So everything is working correctly. Excellent. So in summary, we've learned about the world position versus the screen position for a prop, and how that's related using the map position, or more accurately, the night's world position. We created a render function and drew the prop texture to the screen for a prop that we created. We're now able to decorate our world with props. Great job. I'll see you in the next video.